Alrighty. Okay, so review session. Yeah, so this review session will be, I'll do a bunch of like content reviews and some practice problems from past exams. And at the end, if we have like leftover time, it'll just be like office hours. You can ask questions. Yeah, and if you have any questions at any point, you can put in the chat, or people here can raise their hands. Also, okay. Can you post a PDF? Do we have that access to that final? I'm not. I didn't even know we had that final. Question mark. Math 103. Oh, final exam fall 2020. I don't know if I'm allowed to give this out or like put it on my website. So that will be a question for Rimmer. Okay, so let's just start with interval. So put this over here so you can see the chat. I will post them afterwards. Yes. Yeah, I'll post them on my website afterwards, like here where it says notes. All right, any other logistical questions before we get, I heard that according to past years, the final is open-ended, so no multiple choice. It's basically a longer Friday quiz, so like 8 questions.
Iris, I have a question. Professor Rimmer said, he said on Canvas that he will be holding a review sessions as well. Do you know when would that happen and through which link?
Yeah, he said Saturday.
So wasn't it supposed to be Monday today, but it didn't happen, right?
Okay, people are saying it did.
Which
yeah, other
link,
students said it did happen.
And which link did he use? Do you know?
He used the office hours link.
Oh, okay.
And he recorded it too, the students were saying. Yep, oh, here it says Monday's review recording. So yeah. Oh yeah, he put the logistics here. 8 questions, open-ended, 100 minutes, cheat sheets. Final exam is in person on Monday, the 20th at 9 a.m. All right, any other logistical questions? Okay, so let's get started then. So at the very beginning of the semester, we started with interval notation. So there's a few questions on the quiz about like transforming set builder notation into interval notation. So here I have an example. So if you're given this set builder notation, z going from, this is z such that this equation has to be held. So this is like the restriction of your variable. So in order to discover what restriction z has, we want to take this restriction, this inequality, and solve for z. So first I subtract 5 from both sides so that I get 6 natural log z is greater than -3. And remember, we want z by itself. So I divide both sides by 6 to get natural log z is greater than -1/2. Then because we just want z by itself, if we take e, the power of e to both sides, then by the 1-to-1 property, this e to the natural log z becomes z by 1-to-1 property. So z is greater than e to the -1/2. And how would you write that in interval notation? Well, we know that this variable z has to be greater than some number, this e to the -1/2. So if we have e to the -1/2 here, we know that z has to be greater than that. So how could you write that in interval notation? Well, there's no bound here. It just keeps going on and on to infinity. So we write it with open bracket e to the -1/2 to infinity. And I picked z because it doesn't really matter what variable you use here. It could be b or p or anything. Okay, any questions on that example? It's from a long while ago. Okay, let's do another example. So if we have this, so here I changed up the variable name. I made it A. It doesn't matter what letter you call it. So A such that this equation is held. And we want to write it in interval notation, meaning what values of A can we have? So again, we have to solve for A. How do you solve for A? Well, we have this inequality. Let's multiply both sides by 3 so that we get 15 minus e to the 2a plus 1 less or equal to 12.
After this math ends.
Then you subtract 15 on both sides, that you get this line. Now, if you divide both sides by -1, you have to remember to switch the inequality sign. When you divide by a negative sign,
Okay, here, let me see.
this inequality switches. So you get this is greater than equal to 3 now. Now, how do you get A equals something? Like we want A on the bottom. So by the one, if we take the natural log of both sides, bless you, then by the one-to-one property, this becomes just 2a plus I. So now we have 2a plus I is greater than equal to natural log 3. Subtract 1 from both sides and divide both sides by 2. So that you get A is greater than equal to this natural log 3 minus 1 over 2. Okay, also fact, I keep referencing the one-to-one property. You should be familiar with all the natural log rules, like natural log e to the a equals a, e to the natural log b equals b. The same with like log rules, log a to b equals b, etc. So those are all like the one-to-one property natural log rules that I'm referencing. Do I probably have them somewhere? Maybe not. Okay. And then so we have A is greater than equal to this number. So think of this whole thing as just a single number. What does it mean for A to be greater than equal that number? Well, it means that if you have A is whatever this natural log number, minus 1 over 2, then it could be, just has to be greater than equal to that. So you have this number all the way to infinity. Any questions on interval notation and set builder notation? Okay. Also, wait 1 second. I think I'm gonna. Okay. So then the next topic we should talk about. Oh, wait, let's do this one. So if you wanted to transform this description into set builder notation now. So this is kind of going opposite. And you wanted to write it so that it describes all multiples of 3, including 0. So like the possible numbers that you can have are like -6, -3, 0, 3, 6, 9, etc. How would you write that in set builder notation? Well, there's one way you could write it. We notice that they're all multiples of 3. So like this is 3 times 1, 3 times 2, 3 times 3. So we need 3 times some number k. Like that's how you get each of these numbers. What is k? Well, if you did -2, you'd get -6. If you did 3 times -1, you get -3, and so on and so on. So k should be numbers like -2, -1, 0, 1, 2. What are those? Those are all integers. So we say that the set builder notation is 3k such that our k variable is an integer, or it's in the set of all integers. Okay. Any questions on that? Okay. And let me know if I'm going too fast or too slow. Okay. The next topic was free and bounded variables. So how do you tell if something is free or bounded? So it didn't come up in the quiz, but I thought I'd just mention this here. Yes, I will post this after the review session. Okay. And I'm also hopefully recording this. So yeah. I think it's being recorded. Okay. Yeah, and everything's on my website. So yeah. Okay. So how do you tell if a variable is free or bounded? Well, if it's free, it's usually going to have like no limitations. It could be anything. So for example, f of x is x squared plus 2. Well, here x is free because we're not limiting x. X could be negative infinity. It could be 0. It could be 100. Doesn't matter. So x here is free. However, over here, as we see, we're defining f of x. So this is the weird like symbol of the dot dot equal. That's like a definition. F of x is defined as x squared plus 2. But if we change this to, let's define it with just a different letter, like u, it means the same thing. So the expression doesn't change if you swap out another variable. So there's this like limitation. This variable will always just be some variable. So x here is bound. So the main difference is that, is there limitations or not? If there is not, the variable is bound or free. If there are limitations, then the variable is bound. Also, especially if it gives you like an interval, like, oh, x can only be within this interval, then you know it's definitely bound. Like it can't be anything it could possibly be. Okay. Next, we have some properties of functions. So this also showed up in the even odd part showed up in past quiz. But let's start. Yeah, let's start with even or odd. So quick refresher. How do you tell if a function is even or odd? If you plug in negative x and you get exactly the same equation, it has to be exactly the same, then your function is even. If you get exactly the opposite, meaning you have to get exactly like negative of your original function. If there's even one slight sign difference, then it's not exactly the opposite. It has to be literally negative of your original function, then that function was odd. Now, if you don't get the same equation and you don't get exactly the opposite, then it's neither even or odd. Also, when you're finding if a function is even or odd, sometimes for the trig identities, it's a little bit tricky, because if we were just given like a polynomial, like f of x is like x squared plus 2, then when we plug in, or let's do x cubed plus 2x, then when we plug in negative x, we get negative x cubed plus 2 times negative x, which is negative x cubed minus 2x. And this is exactly negative of our original function. So this function was odd. So that's more clear to tell because they're polynomials. You can take the negative of everything. But for trig, it might be a little bit trickier. Like if you're just given in orange, f of x equals sine of x, then is sine of x even or odd? When you plug in negative x, you get sine of negative x. But what is sine of negative x? Is that the same as sine of x? No. Is it exactly negative of it? Well, it doesn't look like this, negative sine x. It doesn't look like this. So how do we know? Well, you have to remember the special identities where sine of negative x is actually the same as negative of sine of x. So in fact, it is exactly negative of your original function. So it is even. Wait, odd. It is exactly negative of your original function. Okay, so what about this example here? Okay, we have, usually you can also tell by the exponents. If all your exponents are even, it's most likely that you'll get the same exact function back. If they're odd, most likely you'll get the opposite function back. So when you plug in negative x here, negative x to the fourth, what is that?
Going over the beginning. Yes, I heard.
Even or odd?
I know how to
What?
do that. Did you want
What? Yes, did someone want to say something? Okay.
He does not want to study. Is it a TA? Like she like it's public, like
Yeah.
You said
Someone's
so?
not muted if should I? Okay. So okay, so yeah, so you plug in negative x, you get, it turns out that it's exactly the same thing, so it will be, this function is even. Any questions on even odd stuff? All right, so symmetry, this didn't show up on the quiz, but just in case, how do you determine if something is symmetric about the x-axis or the y-axis or the origin? It's similar to even and odd, except you will need to replace different things. So if you replace every single y with a negative y and you get exactly the same equation, then it's symmetric with respect to the x-axis. If you replace all the x's with negative x and you get the same equation, that means that it's symmetric about the y-axis. If you replace x with negative x and y with negative y and you get the same equation, then you know that it's symmetric about the origin. So as an example, or the most simplest example is x squared. We know that's symmetric about the y-axis, but why is that? Well, it turns out if we replace the x's with negative x, we get the same exact equation back. So it's symmetric with respect to the y-axis. Okay, then, okay, this turned up big in the quiz, which were transformations. If you have an original function and you're trying to find some other function using transformations, you should remember what are the different patterns. So if you're just adding a number, you have some function, you're just adding a simple number, that will be a vertical shift up or down, depending if you're adding or subtracting. Now, if the change is within your x, like within your input, that will tell you about if you're horizontally shifting right or left. Reflection about the x-axis, you should look at negative signs. So for example, we have f(x) is square root x. And h of x is negative square root x. Well, what happened between these two? Well, h of x is exactly negative of your original function. So it's a reflection in the x-axis. But if the negative sign were inside, that's what it means for your input to have a negative x. So meaning that you're plugging in negative x wherever you see an x, and you get this h of x. So this will be a reflection in the y-axis. So this is this, and this is this. Okay, and the same for vertical shrinks and shifts. You should note that depending on this constant, if it's greater than 1 or less than 1, it will tell you if it's shrinking or stretching. Okay, so I have an example here. Oh, any questions on the rules? Yeah, I'll put it on my website. Okay, so here is an example from chapter 1, Sum Problems, number 1. So they give you this graph of cosine x plus x to the 2/3, like this. And they want you to sketch these other functions. So how do you know what is going on? Well, for the first one, notice the patterns. For this first one, the only difference here is that for each input, like for x's, we have x plus 1 instead. So that means we're plugging in something else. What does that look like if we're plugging in something else? Well, that looks like this, right? We're plugging in something else for our input. And so what is this? This is horizontal shift, right or left. So because this is a +1, according to our shifts here, this will be a horizontal shift left. And that's what exactly it is. It's left 1 unit because we plugged in x plus 1 instead. And according to our rules, that's shifting left. What about this next one? Here, the only difference is that we're dividing by 2 now. So we're doing half of that. What rule does that look like? That looks like one of these, because here you have c of x, and our c here is 1/2. So that fits this category. So it will be a horizontal stretch, like so. And what about the last one, part C? We have the same exact function, but now the same exact function overall divided by 2. So what will that do? Well, now our scalar, our C, this dividing by 2, is on the outside of our original function. So we should be using these rules here, these vertical stretch or shrink rules. We're dividing by 2, or you can think of it as multiplying by 1/2. What is 1/2? 1/2 is between here. So it's a vertical shrink. So that is the third one, vertical shrink. Any questions on this?
I have a
sample?
question.
Yeah.
If like, how would in one of these equations, how would a reflection in the x-axis or y-axis look like in this problem?
Mhm.
In
So
your
yeah.
example, like,
Okay, so reflection in the x-axis is you start with your original function and you take the negative of all of it. So our original function is cosine x plus x to 2/3. So if you took the negative of it, so it would look like negative cosine x minus x to 2/3. That would be a reflection in the x-axis. For a reflection in the y-axis, it would be, so reflection in y-axis, you're plugging in negative x as your input. So you would have cosine of negative x plus negative x to 2/3. That would be reflection in the
Got it.
y-axis. Yeah.
Thank you.
Any other questions on this? Okay. So what about finding inverses? So sometimes inverses are also a bit tricky, but if you had this function f of x equals square root of 2x plus 3 minus 16. So, okay, I just used Desmos and graphed it, but say they asked like sketch it, you'd have to start plugging in numbers and roughly sketch what it should look like, which I have there, and also sketch its inverse, which I also sketch. What do you know about the inverse? The inverse is always symmetric with reflection, symmetric about the origin to your function. So that's how you can always sketch your inverse. How would you find the inverse? So our original function was y equals square root 2x plus 3 minus 16. What's your first step? You switch the x and y. So wherever I see a y, I'm going to put x instead. Wherever I see an x, I will put y instead. So now we get this first line, x equals square root 2y plus 3 minus 16. Now we want to solve for y. So how do we solve for y? You can add 16 to both sides, square root both sides. So we are at this line. Then you subtract 3 on both sides. So you get 2y equals this x plus 16 squared minus 3. And then you divide both sides by 2. So you get this inverse. This is your inverse. F inverse of x is x plus 16 squared minus 3 over 2. What if it asks for the domain and range? So remember that if you have your original function, original f, let me write this in purple. If you have your original function and your domain is like AB, your range is CD. For your inverse, the domain and range is switch. So inverse, now your domain is the CD, and your range is your AB. So if you're ever unsure what the actual domain or range of your inverse is, just look at your original function and switch them. So what do I mean by that? For f of x, our original function, it looked like this. So the domain here is from whatever this point is to infinity. How do you find that point? Well, we know that if this is our original function highlighted in yellow, we're not allowed to take the square root of a negative number. So whatever's under here has to be greater than or equal to 0. So if I set that greater than equal to 0, it turns out that x has to be greater than equal to -3/2. So our interval
Hello, I don't think we can hear you.
okay. Now can you hear me? Wait.
All right, you're all good now.
Okay. Okay, I think the Wi-Fi is like. All right, so sure. Oh no, the audio is for my iPad. Oh, okay, now it's working.
I have a question.
Okay, cool. Yeah.
How did you get the range problem again?
Yeah. So the range here. So we found the domain. It's -3/2 to infinity. For the range, we know that whatever is under here, it's gonna have to be a positive number, or the smallest it could be is 0. So the smallest number possible for y would be 0 minus 16, which is -16. So it can be -16. But imagine you have some other number here. Say this turns out to be 1. Then you get 1 minus 16, which is -15. -15 is greater than -16, so it's within here. So the smallest number you could get is -16 all the way up to infinity. Yeah. That makes sense?
Yes.
Okay. So then what is the inverse of -20? Well, we just found out that the domain of your inverse is from -16 to infinity. So you can't even have, this doesn't even exist. You can't do the inverse with -20 plugged in because it's not in your domain. But what you can do is -15. So how would you find the inverse of -15? Well, we look at what was our inverse equation. It was up here. And we just plug in -15. So you plug in -15 plus 16 squared minus 3/2. So that gives 1 minus 3/2 or -1. Okay, any questions on this example? Okay, where does still have battery? Hopefully it works. Okay, so next, oh, I did write all the log rules. Okay, so these are all the exponential rules. Just to summarize, I just thought I'd add them here as a important thing to know if you're not comfortable with it yet. So all the exponent rules, all the log rules. This is the inverse property I was referring to, where log base a of a to the x equals x. Same with natural logs. More properties of logarithms and the change of base formulas. So these are just all formulas I thought I'd list. But Does anyone have any questions about the formulas themselves? Okay, so then all the questions, next topic is all the questions about if you do something to X, what happens to X? Like all those types of things. So here I have an example. If e to the x is multiplied by 8e to 9, what happens to x? So how do you approach this problem? We have, this is our original function, this e to the x, and we're multiplying it by this red thing. What happened to x? Well, this should equal e to the something, and we want to find out what happened to that x. What did this become? So we have to make all of this thing on the left side. We want all of the left side to be e to something so that we can find out what happened to that x. So how do we do that? Well, at this line, I'm just going to rewrite it so that I move this scalar out here so that we have 8 times e to the x sub 1, e to the 9. Now, exponent rules. Here we have the same base, so we can add the exponents. This is e to the x1 plus 9. But now we have this 8 out here. We don't want this random 8 here. What is 8? 8 is the same thing as e to the natural log 8 because of the inverse property that I mentioned. So writing this highlighted thing is equal to 8. Now we have both bases being e, so the exponents, we can add them. So we have e to the natural log 8 plus x1 plus 9. So what ended up happening to that exponent, that x? Well, we added natural log 8 plus 9 to it. So that's what happened to x. Any questions on this example? Okay. Maybe I should. Okay, so there's also questions about like how many digits does this number have? How big is it? What is it approximately equal to? So first, let me just say that if you have something like 10 to the 5, how many digits does that have? Well, 10 to the 5 is there's 5 zeros. 1, 2, 3, 4, 5. That's 6 digits. So if we just know in general that something has 6 digits, we can do 6 minus 1, which is 5, and just write it as 10 to the 5th, just in general. We know that if something has 6 digits, it's going to be like something times 10 to the 5th. So that's some intuition. So if we have that h is a 50-digit number, we can write h as 10 to the 49, because that means that there's going to be 50 digits in this number for h. Then they ask, what is natural log h approximately equal to? Well, if you take the natural log of both sides, you get natural log, now what is natural log h? Natural log h is, you plug in h, which we just said is 10 to the 49. Then natural log rules, this exponent here you can bring down. So we bring this 49 down so that we have 49 times natural log 10. Now, in the textbook, there's a chart of like natural log and what they're equal to. So natural log 10 equals 2.3 from that textbook table. So we get 49 times 2.3, which is about 112.7. So that's approximately what natural log h is equal to. Yeah.
Should we probably write down the values of natural log on our cheat sheet?
Yeah, I would, especially natural log 10, I think, has been used a lot. Okay, and then what about part B? So estimate the number of digits that 8 to the 20 has if you are given this fact. So how many digits does 8 to the 20 have? Well, how do we want to approach it? Like, we don't want to do 8 times 8 times 8, etc. But we know this intuition from our beginning. So we want to write 8 to the 20 somehow as 10 to the something. So that way we know how many digits there are. So the idea is, how can we rewrite 8 to the 20 so that it looks like 10 to the something? And then once we get 10 to the something, you add 1 to that exponent to see how many digits there are. So, well, we're given this fact, so why don't we take the natural or the log base 10 of 8 to the 20? We get this highlighted yellow thing, but the highlighted yellow thing is not equal to 8 to the 20. How do we make it equal to 8 to the 20? We have to do 10 to the power of that. Because without the 10, this is a completely different number. Like, we don't know what that is. But if we do 10 to this, by the inverse property, this is equal to exactly 8 to the 20. So now we have what we want. We have 10 to the something. But what is this something? Well, by natural log rules again, we can bring this 20 down. So we have 10 to the power of 20 times log base 10 of 8. What is log base 10 of 8? We were given that it's 9/10. So we were given here that it's 9/10. So we have 10 to the, let's simplify this. So this becomes 1, this is 2. So 10 to the 18. And how many digits does 10 to the 18 have? Well, that's 18 zeros and a 1. So 19 digits. So 8 to the 20 has 19 digits total.
I have a question.
Yeah.
Can you explain the first part again? How 8 to the 20th is equal to 10 of log? Can you explain that part?
Yeah. Yes. Okay, so we want to write, so 8 to the 20. There's just looking at 8 to the 20, there's no way we can do anything to it. But we know that a bunch of log rules can simplify things for us. So the first thought is, what if we take the log base 10 of it? Sure, because this, with log rules, we can bring the 20 down, etc. Maybe simplify things. But log base 10 of that is not equal to 8 to the 20. So if we just evaluated this, this would not be doing anything. This would be doing like finding how many digits of a whole other number. We need these two to be equal. So in order to make them equal, we have to do 10 to the power of that. Because by fact from the natural log rules, we know that a to log a of b equals b. So now if we take it 10 to the power of that, now these two are equal. And now we can work with this thing on the right side.
Got it. Okay, thank you.
Yep. Any other questions on this example? Okay, so what about limits? So should I? Okay, I will erase this. Okay, so limits. Just quick refresher. What does it mean for something to be a horizontal asymptote? It means that your limit as x goes to infinity should equal some number. And as it goes to negative infinity, it should also equal that number. What does that mean? If we have a graph that looks like this purple one here, this has a horizontal asymptote at x at 0, at y equals 0. Because as x approaches infinity, it gets closer and closer and closer to 0. So this limit equals 0. Thus, there's a horizontal asymptote at 0. So that's what it means to be horizontal asymptote. Now, so this was from the fall 2011 exam, number 7B. So how would you graph this? So I know a lot of the past exams are all multiple choice, but if you just take away the multiple choice, a lot of them do become open-ended problems. So I would still recommend looking at past exams. So we have limit as x approaches 0 from the right side should equal -3. So as x approaches 0 from the right side, you should be approaching -3. So something's happening over here. We don't know what's happening, but we know that as it approaches 0 from the right side, you should hit -3. I'll put an open circle there for now. But we don't know what else is happening over here. Okay, what about this one? As it approaches 0 from the left, it should equal 2. So whatever's happening over here, we don't care, but it's gonna approach 2 from the left. So something's happening over here, we don't know. But as it approaches 0 from the left, it's going towards 2. And it doesn't, what does it mean for a limit to equal something? You don't have to actually have it defined here. It could be an open circle. The limit of something is just looking at what number you're approaching as x goes to that number. Okay, then f of 0 equals 1/2. So f of 0 equals 1/2 is like here. As x approaches 3, it should be going to infinity. What does that mean? That means at x equals 3, there should be a vertical asymptote. Okay, what does it mean for f of x as x going to 3 to be infinity? It means that as you approach 3 from the left, you should get infinity. And as you approach 3 from the right, you should also get infinity. That's what it means for a limit to be something. So from the left, you're going to get some infinity. From the right, also some infinity. So keep in mind that this is all very rough. I'm drawing roughly what it should be, and then we'll fix it. Okay, and then as x approaches infinity, it should equal 0. So we know that it should go somewhat like this, because as x gets larger and larger and larger, it gets closer and closer to 0. Then what about this final thing? As x approaches negative infinity, it should equal 1. So something, as x approaches negative infinity, it should be going to 1. So you have like some asymptote here. So maybe instead of this green thing that we didn't know what was happening, let's make it be like this. That way we keep our limit going to 0 from the left, it's still 2, but also the limit going to negative infinity is now 1. Okay, and then let's fix up this blue line here. So I'm going to connect this blue and this orange, because remember the blue, we didn't know what was happening. As long as it goes to -3, we're good. And that completes our graph.
I have a question. How do you know that
Yeah.
this circle is the circles are open?
Because in order to be a function, it has to pass the vertical line test. So you can't have it defined at more than 2 points. We already have it defined at the purple point here. So we can't have it be like f of 0 is 1/2, f of 0 is 2, f of 0 is -3. You can't have that to be a function. So that's why it has to be open circles. Yeah.
And also, can you please put the link for the notes on the chat?
I haven't posted them yet. I'll post them after this review session.
The last limit condition.
Uh-huh.
why
And
is
then
it-
where do we find them?
On my website. Sorry, someone in person is asking a question real quick.
So, the last limit condition, why is it that you can have like arrows cross over it, like the orange arrows? Like the
Mhm.
purple one, I understand that it goes to,
Mhm.
or that there's like an asymptote there,
Yes.
but I just always remember like you can't have like anything cross over it.
Uh-huh. Oh, I see. Like this line,
Yeah,
I
like,
guess.
if you extended the asymptote.
Yeah. So that's like the horizontal line test for seeing if something has an inverse. But it's okay in this, like we're not really extending it. This is still true that this is an asymptote, because we only needed that x going to, okay. For it to be an asymptote, you would need x limit as x going to infinity of f(x) to also be 1. I think that's what you're thinking of. So it would be like this and this. Yeah, but right here, it's only specifying one part, the negative infinity. So it's okay. We just have it on this half. We don't need another thing on this part.
Okay.
And we needed it to be like that, otherwise, because if you imagine having like another purple line here, then our thing wouldn't be a function anymore. It doesn't pass the vertical line test. So it would not be a valid function. Okay, other questions on this one? Okay, and Michelle, the notes will be on my website. So wherever link my website thing is. Okay, I just put it in the chat. Okay, so then what about finding limits? So next topic. So there's two types of limits. First limit is you're finding a limit at x equals some number. So how do you do that? First thing you want to try substitution. So plug in that number x equals a and see if you get anything. If you plug in that number and you get 0 over 0 or some infinity over infinity, like an indeterminate form, that means that you have to use L'Hopital's rule. L'Hopital's rule says you take the derivative of just the numerator, derivative of just the denominator, and take that limit. So you're not doing any quotient rule or anything. Just look at the numerator itself, take the derivative. Look at the denominator itself, take the derivative. And L'Hopital says that doing this limit is equal or is equivalent to doing the original limit. What if you don't get 0 over 0 or infinity over infinity? Then you need to try some other like simplifying tricks to try to see if maybe something will cancel out or something will work out nicer. So there's tricks like multiplying by the conjugate. You should know how to do that. Multiplying by least common factor, so that maybe you get a common denominator or things cancel out. And you could also try factoring. And even some weird ones factor, like if you had 4 minus x, that actually factors to 2 minus square root x, 2 plus square root x. So factoring doesn't always have to look like x squared minus 4, which is x plus 2, x minus 4, or x minus 2. Okay, so that was just like a little flowchart thing. This x does not have a square root. Yes. Okay, the second type is limit as x approaches infinity. So that was for x is some number. If you had x going to infinity, the main important rules are these third bullet points or this bullet point. So if the degree of your numerator is greater than the degree of your denominator, that limit will be does not exist or diverges. If the degrees are equal, then the limit will be whatever coefficients of the highest degree variable you used. If the degree of the numerator is less than the degree of the denominator, then the limit will converge to 0. So these are the common rules for x going to infinity.
Wait, can we get an example for the one where they're equal to each other?
Yeah. So let's do like oh yeah. Wait. There's like a quiz example. Wait, let's look at one of the quiz examples actually. There's a really good one. Somewhere.
So do you know if we'll get quiz 9 and the last redo that before?
He said that like possibly we have to do that.
Okay.
Yeah, we'll get them back for we are not sure soon though. I think quiz 9 is almost graded. We're waiting on rumor for that. Okay, wait, okay, I promise this is a good example.
I know which question you're talking about.
Yeah.
Just like the last question. Is there a or somewhere else into it? So,
Mm-hmm. There's a really good let me think. Where was it though? Wait, let me think. What was thinking. Oh wait, it was this one. I'm thinking. So for example, limit as x going to infinity. So this is quiz 3, problem 2. So example, you have limit as x going to infinity of x square root 16x squared plus 11x minus 4 over 2x squared. Okay, so this example by itself, if you look at the powers, here we have this x squared, but then square root. So this is technically like contributing an x, and this is contributing an x. So in the numerator, your degree is 2. But in the denominator, your degree is also 2. Denominator equals 2. So your degrees are equivalent, so you take their coefficients. So where did our degree from the denominator come from? It came from the 2x squared. So we're gonna want to use this 2 here. Where did our degree in the numerator come from? It came from this 16x squared square root multiplied by an x. So our coefficient here is this square root 16. So that's 4 over 2, which is 2. So this limit is 2. But so this is just telling you like an idea of what your answer should be. But to show your work, you should show what Rimmer has in the answer key, where what he does is he tries to get it simplified, like he gets it all simplified so that you're left with just an x on top and the bottom multiplied by some number. Because since these are the same degrees, you're going to want to take the coefficients. So you want it as simple as possible. You just want these numbers here, these scalars. How do you get the scalars by itself? Well, so we have this x square root, so we have x. We want an x to come out. So that way we know like the power is x squared. So how could we do that? If we factor out this x squared, we get 16 plus 11 over x minus 4 over x squared. Why is that helpful for us? Because think about if you did square root of 4 times 3, how would you write that? You'd write it as square root 4 square root 3 or 2 square root 3. So if we do the same thing here, we get limit as x approaches infinity of x, we get square root of this first thing, square root of the second thing, all over 2x squared. So now this square root x squared, that's x. So x times x is x squared times this square root thing all over 2x squared. Now, when you take the limit as x goes to infinity, remember the infinity rules. So here, this 11 over x, as x goes to infinity, this limit is 0. Because the degree of the top is 0, degree of the bottom is 1. Numerator is less than the denominator, so it's 0. This term is also goes to 0 as x goes to infinity. Because the degree of the numerator is less than the degree of the denominator. So what you're left with is the limit as x going to infinity of x squared square root of 16 to x squared, or this is 4x squared over 2x squared. Now the degrees of x are literally exactly the same, so it's more clearly seen that you can take the coefficients, which is 2. Yeah.
And then 4x times x squared, and only the highest degree matters.
Mm-hmm.
Would you cross out saying that like
Um. I think this is definitely a better way. If you do it like this way at the beginning where I just said like, oh, this is this and this, I'm not sure if you would get full credit if Rimmer graded it. But if I did, maybe. How would you show your work if you use asymptotic analysis? What do you mean how would you find this answer using that? No, I cannot hear you.
All right, is that better? All right, yeah, that's better. Okay.
Yes.
So basically, what you can do is, I remember you can if you take the original expression that you get, you can basically just say that the limit as x approaches infinity of 16x squared plus 11x minus 4, obviously under the square root, just equals the 16x, the limit as x approaches infinity of 16x squared. Because I think somebody in person also mentioned this, that like the 11x minus 4 doesn't really matter because it just behaves in the same way. So yeah. So like how exactly would you show that? Would you just show that like with this?
Yeah, I think that would be showing that would be this, like what you're saying, because this is showing that, oh, this part and this part doesn't matter.
Okay. All right, thank you.
Yes. Yep. Okay, any other questions on this limit stuff? Okay, so let me see. I have a few more examples, but let me, because I have a few more slides. Okay, let's do a. Okay, does anyone want to do a super hard limit problem or move on? Okay. Okay, so if we wanted to find the limit of this function, how do you do that? First thing, always try to substitute first. So we substitute x equals 0. What do we get? You plug in 0, you get, so if you do the algebra, you get 0 over 0. If you get 0 over 0, that's the indeterminate form, which means we want to use L'Hopital's rule. So let's try using L'Hopital's rule. What happens? You want to take the derivative of just the top. How do you take the derivative of this top numerator? Don't forget, you have to use chain rule for this. So chain rule says, do the derivative of your outer function, which would be 3/2 something to the 1/2. You plug in your complicated thing, which is 1 minus cosine x. Then by the chain rule, because this is some complicated thing, you also have to multiply by its derivative. What is its derivative? Sine x. So this is the derivative of just the top. For the bottom, what's the derivative of x minus sine x? You can think of it separately. Derivative of x is 1. Derivative of sine x is cosine x. So this is the derivative of that. Okay, and then I just rewrote it a bit because I saw this 1 minus cosine x on both the bottom and top. So I just simplified it to this purple thing. So yeah, because here there's like an implicit 1. So if you did 1 minus half, you'd be left with a half in the denominator. So now we get the purple thing. So usually once you get this L'Hopital's, you use L'Hopital's, you get something, you plug in 0. We plug in 0 again. But we run into another problem. We get 0 over 0 again. That's the indeterminate form. So you might be like, L'Hopital's second time, maybe. So try L'Hopital's again. We take the derivative of the top. We get 3/2 cosine x. Take the derivative of the bottom. you have to use chain rule again, which is highlighted in green. So to do that, you do derivative of the outer function. You bring the half down of this complicated thing to the negative a half. Then derivative of your inner function. Derivative of 1 minus cosine x is sine x. Okay, so now we tried L'Hopital the second time. We want to plug in 0 and see what happens. When we plug in 0, you simplify, we get 3/2 over 0. Uh-oh, that's a problem because we are doing L'Hopital's rule. We were supposed to find something, but now we're getting this like error, divide by 0 error. So we need some other choices, like L'Hopital's ended up not working. Well, let's go back to this purple thing. Like after we did L'Hopital's once, we got the purple thing. Let's not do L'Hopital's rule again. Let's try something else with this purple thing. So here we have the purple thing. What if we try simplifying so that maybe something will happen? Well, this 1 minus cosine x, this thing is weird, right? Because if we plugged in 0, that's what's making us get 0 in the denominator here. So why don't we multiply by 1 plus cosine x to the 1/2? Kind of like doing conjugate, but not exactly. But what if we multiply top and bottom by that? So we have orange. Then now let's simplify. So we have in the top, we have the purple times the orange. In the bottom, how do you get, what is this highlighted times this highlighted? Well, if you think about how would you do 3 times square root of 2? That would be square root of 3 times 2. Like that's what you would do. So we can do the same thing here. We're going to multiply those inner things, the 1 minus cosine x and the 1 plus cosine x, and take it all to the half power. So now what we get in the denominator is this 1 minus cosine squared x. Well, does that help us anywhere? When we plug in 0, we still get cosine of 0 is 1. We still get 0 in the denominator. But trig rules. Most common one to know is sine squared x plus cosine squared x equals 1. So what is 1 minus cosine squared x? Turns out to be sine squared x. So if we substitute that in for this, we get sine squared x to the 1/2. What is sine squared x to the 1/2? That's sine x. And look, something canceled out. This sine x canceled out. So we're left with 3/2 times this 1 plus cosine x to 1/2 power. Now we can try plugging in x equals 0. What happens? Well, we get cosine of 0 is 1. So we have 3/2 times 1 plus 1 to the half, or 3/2 times square root 2. So our final answer was 3 times square root 2 over 2. So that was the tricky one where using L'Hopital's didn't end up working as we wanted. Any questions on this example?
I have a question.
Yes.
So when we first multiplied it by 1 plus cosine x to the 1/2, right? Why did we decide on that? Like, I get everything else, but why did we decide on that specifically?
Because our problem was coming from this 1 minus cosine x to the half. Like when we plugged in 0, we kept getting 1 minus 1, which is 0. Over here, we also had, even when we took L'Hopital's again, we had this 1 minus cosine x here. That was causing our trouble. So we don't want a 1 minus cosine x. So we decided to get rid of it by multiplying by 1 plus cosine x. Because if I multiply by 1 plus cosine x, that ends up giving me 1 minus cosine x squared, which is slightly better because by using a trig rule, that is sine squared x. So we got something else. We don't want 1 minus cosine x because that was causing our zeros happening.
Got it. Thank you.
Yep. Any other questions on this? Okay, yeah, let that sink in. But let me move on to continuity. So here I just relisted some important things to remember. For a function to be continuous at some point C, you need 3 criteria to be met. Your function at that value has to be defined. So you have to have like C f of x, has to be some point. The limit as x approaches C of that function should exist. And third, that limit should equal what it was defined at. That's what it means for it to be continuous. And here I have some other continuity rules that might be helpful, like continuity of compositions or inverse functions. But those are just some rules. Let's do an example. So this is from fall 2011, number 3. Oh, okay. So say this was a different question. Say they asked, what are some values where the function could be discontinuous? Usually a function is discontinuous at whatever these like interval endpoints are. So like the most obvious one would be -1 and 2. Those are the ones you should be suspicious of. Other places where discontinuities could happen is if your function isn't defined somewhere. Like if you had a 1 minus x here, then yeah, it would be discontinuous at -1, but it also might be discontinuous at 1. If this 1 over x was here, actually. So looking for discontinuities. Okay, let me make this like purple. Interval endpoints and where function is not defined, like for 1 over x. Okay, so what this question is saying, find the values a and b such that the function is continuous. What does it mean for a function to be continuous? Well, the limit should exist and they should flow nicely. So like if say a was like this curve and b was this curve, we see that these 2 points should meet up in order to be continuous. Because if it was instead, this was our b curve, that would not be continuous since the limits are different, or the limit does not exist. So wherever this -1 plugged into our first line, which I call A, and plugging a -1 to our second line B, they should be equal. Those 2 points should be equal so that it flows nicely and it's continuous like this. So we plug in x equals -1 to A and we get 8. If we plug -1 into B, we get A plus 3. And we want those 2 to be equal. So we want 8 to equal A plus 3. You solve by subtracting 3 on both sides, you get A equals 5. So the correct answer for A is A equals 5. But what about, how do you find B? So what values of B so that this function is continuous? Well, when we plug in 2 to C, it should equal if we plugged in 2 to B. So what does that mean? For B, we had a x squared, so plug in 2 for x, squared plus 2 plus 4, that's 4a plus 6. What was A? We just found that A was 5. So 4 times 5 plus 6, or 26. What if we plug in 2 to C? We get 2 to the 2 plus B minus 6. And we want to set the green equal to the orange. So we set the green equal to the orange. How do we solve for that? You add 6 to both sides. So you get 32 equals this. What is 2 to the 2 plus b? Exponent rules, it's the same as writing 2 squared, 2 to the b. Because they have the same base. So you would add the exponents. So what is 2 squared? It's 4. So we divide both sides by 4 to get 8 equals 2b. What is b? b is 3, because 2 cubed is 3. So the correct answer for b was 3, or T. Any questions on this example or these types of examples?
I have a question.
Yeah.
For the first part, how did the -8 to the third power of root of -1 just turn into -8?
Mm-hmm. Yeah. So here we have -8. So I'm plugging in -1 for x. So I have cube root of -1. What is cube root of -1? So we have, this is 8 times -8 times -1 cube root. Well, we want to find what number cubed gives you -1. Well, that's only -1, because -1 times -1 times -1 is, you have negative, positive, negative, which is -1. So -1 cubed, cube root is -1. So -8 times -1, which is +8. Like if you had, what is square root of 4? You want to find what number times what number gives you 4. That number is 2. So similarly, cube root of -1, you want to find what number times what number times what number gives you -1. Well, that number is -1. Any other questions? Yeah.
Why did something it's not, it's like technically it's not in the interval.
Yes, so it's not in the interval, but what is happening is like from -1 to 2. So say it is an open circle, like the orange, and then the green is defined at 2, so it would like plug it in, and you want that point to be exactly the same for it to continue.
Oh,
So yeah, like even though this 2 is not in the interval, but essentially we want it to end up at the same place. Like we're imagining that it's equal to 2 so that we can make sure that this point here is the same point, that they're moving up correctly. So that's why we're plugging in 2 to B, and we're also plugging in 2 to C so that they match up here. So whenever you see these types of questions, it's about plugging them in and setting them equal to each other so that you get, we want this point to be the same. So that's why we're setting them equal to each other. Other questions? Okay, then we have finding derivatives. So you should be especially comfortable with derivatives, and integrals will be the next review session. But derivatives, there's 2 ways. It could ask you to find the derivative using the limit definition, which is a while ago, but it's the limit as h goes to 0 of f of x plus h minus f of x over h. Or second type is just using the derivative formulas. So it could be all different types. You could have derivatives in this chart here. It's like all the trig derivatives, natural log derivatives, inverse trig derivatives. It could ask you to use, like it won't say like use product rule, but you should evaluate and notice that you need to use product rule. So product rule, quotient rule, chain rule, implicit differentiation, and logarithmic differentiation, which are
question here, they'll ask you to use the definition of it and not use just regular derivative rules.
yeah, in like past exams they say like find a derivative using this limit definition.
Any chance we could go per element definition?
Yeah. Let's see. Do I have? Okay. Okay, I'm pretty sure I did. saw someone, or I saw one somewhere. Um, oh, wait. Let me find a. You want a harder one? For average limit of fine. Okay, why don't we do like I don't know. Simple. Find derivative of f of x equals like I don't know, square root x plus 2 minus 3 sine x. I don't know. I just made it up. So okay, maybe wait, the trig might make it a bit difficult. Minus 3 or something. So how would you do that? So f prime of x equals limit as h approaches 0 of. So this is just me writing the formula for h. So f of x plus h. This means that anywhere you see an x, you want to plug in x plus h. So here I see an x. I'm going to plug in x plus h, then plus 2, minus what was our, minus 3. So this is f of x plus h, minus our original function. So x plus 2 minus 3, all over h. What does this give us? This gives us x plus h plus 2 minus 3 minus x plus 2 minus 3 all over h. So how would we do this? Well, we can't like plug in 0 because that'd give us divide by 0 error. We see a square root. Whenever something involves the square root, you're most likely going to want to multiply by the conjugate. So let's try multiplying by the conjugate. The conjugate is this whole thing, x plus ln a plus sign here, ln this whole thing again, over the same exact thing. So the only difference is this plus sign between everything else. So notice that the conjugate is not flipping this sign in here. It's flipping the sign out of two separate things between the two expressions that you have. So multiplying, what does that give you? You could FOIL this. So you FOIL this first term and you get x plus h plus 2. Oh wait, let me do it this. So x squared x plus h plus minus 3 squared. Then you do plus this term minus this term, those cancel out, minus this the two last terms, minus this squared, all over this bottom thing. H plus 2 minus 3 plus square root x plus 2 minus 3. Okay, then you want to try to simplify stuff. Okay. Maybe this. All right, we can do this. So what is this squared? you have to FOIL this inner part now. So this inner part FOILed is x plus h plus 2. This term times the -3 minus 3 times this term. So that gives -6 of the square root thing plus 9. So that's the first thing. Minus, what is this second thing squared? Let me do it in green. Minus, same thing squared is x plus 2 minus 6 times square root x plus 2 plus 9. All over this denominator, which I will copy and paste. Okay, now we have limit as h approaches 0. What is our goal? We want something to cancel out because we don't want plugging in 0 here to make our denominator 0. So let's simplify. You have this x minus x that cancels. 2 minus 2 that cancels. 9 minus 9 cancels. So you're left with h minus 6 square root x plus h plus 2 minus plus 6 square root x plus 2 all over this weird denominator. Let's see. Might not have been good to make up something. Okay, the bad thing about making it up is that nothing cancels nicely. X plus 2. That's 9. Okay, unfortunately nothing cancels. It was basically something supposed to cancel and then you plug it in, it works. Sorry about that. But yeah, whatever you get, now because you know about derivative rules, though, you should always be able to check what is the derivative. What is the derivative of this? Well, if you
Wait,
do the
excuse me.
chain rule, yeah. Go ahead.
Can't you just subtract 3 from? Well, no, in the numerator, you can in the like the second step, you can cancel out that 3, and then because it's like a minus plus minus minus, and then you can cancel out the 3 and then do the conjugate
Oh.
thing, and then that
Uh-huh.
makes it so much easier to just cancel stuff because then the h's just cancel.
Okay, nice. Thank you. So, okay. As Reed suggested, this -3 plus 3 will cancel. Good observation. And you get this over h. Okay, now it looks nicer. Now you multiply by the conjugate. Plus square root x plus 2 over square root x plus h plus 2 plus square root x plus 2. That gives you the limit of, let's FOIL the top. You get x plus h plus 2. This term minus this term becomes 0. So now you have subtracting the last 2 terms. All over h times this blue thing. Okay, great. This is nice. Now we have x minus x cancels, 2 minus 2 cancels. We're left with h over h times this. Now our h is canceled as was supposed to happen. And so you get limit as h goes to 0 over this thing. Now you can plug in h equals 0. So you get 1 over x plus 0 plus 2 plus x plus 2. Let me get rid of this incorrect thing. Okay, so you get 1 over x plus 2 plus x plus 2 which is 1/2 times square root x plus 2. Great, thank you. So yeah, and you can always check that this is in fact the correct derivative because you could use chain rule and see that it's exactly the same. Okay. Any questions on this example? Okay, so tangent lines are also big. So remember, for tangent lines, you need a point, slope, use point slope formula. You should be comfortable with finding that slope. Here we have lots of, or I did lots of examples of the tangent lines, but let me, okay, why don't I do this one real quick? So this is from 2011 so exam again. It says find the value of a such that the tangent lines to x equals a and x equals a plus 1 are parallel. What does it mean for the tangent lines to be parallel? That means that the slopes of both these lines should be equal. So how do you get the slope? You take the derivative. So this, take the derivative of this y and you get 3x squared minus 4x plus 1. When you plug that into a, so I did a bit of unnecessary work here, but when you plug that into, when you plug a into that, your slope at x equal a is this green highlight. You just plug in a wherever you see an x. What about your slope at x equals a plus 1? You get this purple highlight. That show up, okay. You get the purple highlight. And so for the two lines to be parallel, the two slopes should be parallel, right? Because if you have like y equals 2x plus 1, y equals 2x, those lines are parallel. So you want the green highlight to equal the purple highlight. And so we can just set those equal to each other and solve for a. You'll get a equals 1/6. So that was just the concept behind this question. Any questions on this? Okay, so I have a few more examples on those, but I'll let you guys look at that. Let's talk about graphs of derivative. So there's 3 different types of graphs you could be given. You could be given the graph of just the regular function, whatever f function. We can call it distance. You could be given the graph of the velocity or the graph of your first derivative. And this was in one of the quizzes where they gave you the graph of f prime of x. They could also give you the graph of f double prime, or you could think of it as your acceleration. What do those graphs tell you? Well, in your original position or your distance function, the slopes told you if they're increasing, decreasing, and then you looked at the shape to see if they're concave up or concave down. If you're given the graph of f prime of x, that means that whenever you are above the x-axis, that means that your slope or your f prime of x was positive. What does it mean for your slope to be positive? That means that your function should have been increasing because the slope is positive. So increasing. Oh wait, I could have been, okay. What about if your function is below the x-axis? That means that your slope was negative, so it was decreasing. Now, looking, so that was just based on where your y value is on the graph. If you look at the slope of f prime of x, well, the slope is the derivative. So if you took the derivative of f prime of x, that gives you f double prime of x. So looking at the slope of this function tells you if it's concave up or concave down. Like in this green part, here your slope is positive, so you're concave up from this x value equals 0 to whatever this number is. All throughout this orange, you are called concave down. And in this red, you're concave up again. What if you're given the acceleration? So acceleration, now it's if you're above the x-axis, you're concave up. If you're below the x-axis, you're concave down. And yes. Any clarifications on the graphs? Okay. Also we have some like critical points things, which I just copied from the recitation notes, but I think they're good to remember so that you know, even though this is not a relative extremum, like this is not a max or min, but it's still a critical point. Your derivative here is 0. Okay, so that was copy pasted. Here is a nice summary of first and second derivative tests. Yes, first and second derivative tests, like finding where is your function increasing, decreasing, concave down. When is it a relative min or max, your inflection points. So that's a quick summary. Absolute extrema, I also copied here. How do you find relative absolute extrema? You need to look at your critical points and don't forget about your endpoints. Okay, so here's a nice little flowchart also for local relative extrema and an absolute global extrema. Okay, wait, one thing I wanted to say also is that, wait, what is it? For quiz 8, but okay, this is unrelated to the review, but for quiz 8, I thought I would mention it now. I forgot to say. A lot of people tried taking the integral of natural log 8 or natural log x. And they said it was 1 over x. This is not true because what is the derivative of 1 over x? That's the derivative of x to the -1, which is -1 x to the -2. So if we took the derivative of this, we should have gotten back what we were asked to take the integral of. But it in fact is not. So that was a common mistake on the quiz 8 or quiz 9 or something. Okay. Let's do this. Okay, let me do this example. So this was from fall 2018 exam, problem 3, and you're given this function. So what is the integral of natural log x? You have to use integration by parts. So what is which of the following statements is true? So you see how all of these are talking about like inflection points or concave up, concave down. So you know that just go straight, find the second derivative. So you'll notice that this was actually a little bit of work. So it is still expected of you, I believe, but even something as tricky as this. So if you took the derivative of this f of x, you get your first line. After a bunch of simplifying, which I will let you guys look at, you get this highlighted thing. Then you take the second derivative. Okay, now we can do that. You would bring this 3 down to get 192x squared and bring this 2 down to get 192x. Derivative of 13 is 0. And in order to find inflection points or where it's concave up or down, you want to set the second derivative equal to 0. So we set this second derivative equal to 0. What does that give us? Well, it gives us either this first expression, 192x equals 0, or this x plus 1 equals 0. X plus 1 equals 0. So that gives us that our second derivative is 0 at x equals 0 or x equals -1. So now we can check, are they really inflection points? Where are they concave up, concave down, etc.? For that, you need to do the sign chart for the second derivative. So here I make a sign chart. I put in where you found these points, so -1 and 0. Then for these points in between on this line chart, line thing, you plug in different points. So for example, and we want to plug into f double prime for this specific chart. So we plug in -2. When we plug in -2, this first term would give you a negative, negative 2 plus 1 is also negative. So you'd have a negative times negative, which is a positive over here on this interval. What about in between here? Let's test like negative a half. You would get, this would be a negative number. Negative a half plus 1 is a positive number. That's 1/2. So in this interval, you have a negative number. And then what about over here? Let's plug in like 1, for example. You get a positive number times another positive number, which is overall a positive number. So here you change from concave up to concave down to concave up. Thus, you have 2 inflection points. So the correct answer was F has 2 inflection points. Any questions on that example?
I have a question. In the beginning, when you were taking the first derivative, where does that 2 come from? The 2 that comes from after you take the
Here.
Yeah.
Yes. So that's from chain rule. So this whole thing is the derivative of 2x plus 1, 2 plus x1 to the 4th. That's this first part. So for that, because this is some complicated thing to the 4th power, you have to use chain rule to find this derivative. So you take the derivative of your whole outer thing with your inner function plugged in. But because this inner thing is some complicated thing, you have to multiply by the derivative of the orange. Derivative of that is 2. So
Oh,
that's
okay.
where the 2 comes from.
Thank you.
Yep. Yeah. Any other questions on this problem?
Can you not wait to like simplify until after the second derivative? Like just do another chain rule?
Oh yeah, you also could do that.
Okay, and you'd get the same thing.
Yes. So yeah, actually that's a better idea than what I did. So I'm gonna take this purple thing. Purple thing equals 8 times 2x plus 1 cubed minus 48x. Wait a second. Yeah. Plus 5. What is the derivative of that? You can bring this exponent down, so you get 24, 2x plus 1 squared, multiplied by the derivative of the inside, then minus 48. And then now you can simplify it, and you should get the same thing. Plus 4x plus 262 plus 21692. Yeah, you get the same exact thing. So yeah, that would have been a better idea than what I did. Okay, other questions on this problem? Okay, and the final thing I was gonna do was like optimization, but we can leave that for next time. So the next review session is tomorrow from 4 to 6 p.m. That'll be like all integration stuff, summation, etc.
I wasn't able to access the recording this morning.
Let's see. Yeah, recording does not exist. It's probably loading or something. Like it takes a while to upload to the cloud. If it was like a 2-hour-long exam, I guess. But yeah.
I have a
Okay,
question.
whoever wanted, yeah.
This final review notes, are they gonna be up before tomorrow's like review session, or are they gonna be up after?
Yeah, I'll put it up. I'll put it up right now. Like after, right after this.
Thank you.
Yeah. Whoever wanted the 2020 thing, by the way, I can scroll through this quickly. If they're still here. Probably not. Okay. Alrighty. Okay, yeah. Then that's the end of prepared review session notes. Okay. Does anyone have any questions?
Are you gonna post the like fake exam you made so we can do it before?
Yeah, it's not a fake exam. It's just
Or
the
just like
previous-
yeah. A practice.
Yeah.
one.
It'll be the 2018 spring one.
Okay.
2018 spring. Yes. So let me see. Is it the 28th? Yeah. So the exam that I'll go over on Wednesday is spring 2018. Okay.
Where can we find that?
If you search on, I'll post it on my website, yes, also. But if you just search UPenn Math 103 past exams,
Okay.
yeah, it should be like the first link and spring 2018.
Spring 2018.
Yes. Yep, and I will keep posting updates on my website also, so you guys can, yeah, if you have questions, also email me. Okay. Wait, just a question. How did you guys like this format for today's review session? Good or
Solid.
okay? So I'll keep
Good.
the format.
Are you gonna go through the, like, show the problems for last year's final?
Oh yeah. Okay. I'll probably also do that. I didn't realize it was final till today. So okay, I will also try to do that. That'd be Wednesday.
Okay, thank you. Wait, could you possibly like post the questions to do them? Because I don't think I have access to Rimmer's.
Okay. Why don't? All right. I'll just put it on my website.
Okay, thank you.
Yep. Thanks. Oh, wait, let me make a list of things to remember. Okay, I'm gonna do spring 2020, and I gotta post it. Okay, and spring 2018. Okay, my short-term memory. All right. Question. Can we do a quiz for question 2, please? Okay. Quiz for. Wait, is it on here? Quiz for question 2. All right. Oh, here, quiz 4. All right, let me put it in. Quiz 4, question 2. All right. Preference for which one?
I think the one with the second one.
This one.
Yeah.
Okay. So it says find f prime of 0. So first, don't even think about the number. Just find the derivative first. Like that's probably going to be the most points. So what is the derivative of? So let me write it here in purple. F of x equals x 6x plus 27 to the 2/3. So this, tell me what is the first thing you want to do? Like what technique do you want to do, or beginning ideas?
You do product rule.
Yes, product rule. So product rule says you do the first term, so green, times derivative of the orange. So why don't I write d dx of the orange first, just so that we can keep track. So I'm not gonna keep taking derivatives. So first, write product rule. First term times derivative of second term plus second term times derivative of your first term, which is x. Okay, so we have x times, what is derivative of this orange thing? We have to use chain rule, right? Because it's a complicated thing times 2/3 to the 2/3 power. So I keep saying like complicated thing because chain rule in general says if you have some u to the b, I guess, u to the x or u to the b, it would be b u to the b minus 1 in general if u is some expression. Here our u is the 6x plus 27. So if we follow this general rule, what is the derivative of that? You take the derivative normally where you bring this 2/3 down, and the new exponent is 2/3 minus 1, which is negative 1/3. And now you plug in the complicated thing. Oh, I should have written du dx. You plug in the complicated thing, and because it's complicated, you have to take the derivative of that, which is 6. Plus, over here we have the orange again. Derivative of x is 1. So overall, we have x times 2/3, 6 plus 27 to negative third. So I'm just rewriting everything in black. Over here, this 3 and 6 cancels out, so we're left with a 2 on top there. So we have a 4x, 6x plus 27 to negative 1/3 plus 6x plus 27 to 2/3. Hopefully I wrote that. Yes. Now the question was to plug it in at what? 0? So we plug it in at 0. This whole first thing becomes 0. Because you have 4 times 0 already. So no matter what you're multiplying, there's going to be a 0 here. So this is just 0. So what really matters is this part. So we get a 6 times 0 plus 27 to the 2/3, or which is 27 to the 2/3. What is 27 to the 2/3? Well, notice that 27 is 3 cubed, right? 3, 9, 27. So we have 3 cubed to the 2/3. When you're doing this, you're multiplying the exponents. So this is like doing 3 to the 3 times 2/3. Or these 3's cancel out and you're just doing 3 squared, which is 9. Does that make sense?
Thank you so much. That makes sense.
Great. Okay. Any other questions? Like general OH office hours.
Is there any chance we could go over like some old quiz questions?
Yeah, sure.
Like we can't go over quiz 9, right?
Wait, quiz 9. Oh, I think his answers are posted already, so yeah. Yeah, we can go over that. If it's already, yeah, because he already posted the answer to you. Yeah. Yep. And I think even the redo is, or is it not?
Yeah, the redo.
Yeah, so we can go over anything from all past quizzes. All right, so quiz 9. Oh, yeah. Okay. Let me, where's the common error? So, okay, should I do the common error question? This question. So a lot of, yeah. This question. So for this question, you're doing the integral of 18x squared natural log x. Okay, one thing people try to do is, so this is incorrect way, maybe tabular integration. Because they saw you have an 18x squared. If you keep taking the derivative of it, you get 36x, 36, 0. That's nice. Because tabular integration, we wanted to get to 0. And then on the right side, you take the integral of it. And they said integral of that is 1x, natural log x, 1 over x. But you can't, this is not the integral of natural log x. You can't do that. Like maybe you're thinking, yes, the derivative of natural log x is 1 over x. However, then the derivative of 1 over x doesn't give you back natural log x. So using this way to do tabular integration would not be correct. Another way, so type 2 incorrect, maybe you try integration, you realize integration by parts. You choose u equals 18 x squared. Wait, what's the correct? Yeah, 18x squared, and dv equals natural log x dx. However, you also get stuck here because how do you find v? V is the integral of natural log x. It's definitely, v is not 1 over x. So if you did it this way and you said v is 1 over x, that's wrong. You could try it this way, but then you have to find what is the integral of natural log x. Maybe as a side note, if people want what is integral of natural log x dx, you would pick u equals ln x, dv equals dx, so that v equals x, du equals 1 over x dx. Integral of u dv is uv minus integral v du, which is u times v minus integral v du, which is x natural log x minus dx, which is x natural log x minus x. So integral of natural log x is not 1 over x. It's this other thing. Okay, correct way is you wanted to choose u equals natural log x. Because we know the integral of 18x squared. That's better for us to calculate. What is that integral? You add 1 to the exponent. So exponent becomes 3 and divide by that new exponent, which is 3. Oh, wait, sorry, something happened. One second. Okay. So you divide by 3, and that is 6x cubed. Over on the u side, we have du equals, now we know how to take the derivative of natural log x. It's 1 over x. So now by the formula, we do integral of u dv equals uv minus integral v du, which is, now we just plug in what we just found. We have all 4 of our components now. We just have to plug in. So u is natural log x, v is 6x cubed, minus integral v, which is 6x cubed, du is 1 over x dx. Oh, okay. Also another, so we have this left side. Now, a lot of people saw this right side, this 6x cubed 1 over x, and thought it looks like 2 separate functions, like the 6x cubed and the 1 over x. Maybe do integration by parts again. However, you don't need to do another like integration technique because this 6x cubed times 1 over x, you can simplify it so that it's 6x squared. And we know how to take the integral of 6x squared dx. What is that? You add 1 to the exponent, divide by that new exponent. So 6x cubed natural log x. So your final answer is 6x cubed natural log x minus 2x cubed. That's your integral. And of course, it's a definite integral from 1 to e to the thirds. So after you do this, you evaluate it from 1 to e to the 1/3. Wait, is it 1 to, 1 to e to the 1/3. Okay. Any questions on that example? Okay, any other questions? Yeah. For quit, wait.
No, it's fall, like.
Oh, fall. Yeah, fall what? Fall 20. Yes. This one? Wait, 2? Sorry. Fall, 2020? 2013. Yeah, wait. Should be. Fall 2013. Yeah, thanks for me, you guys. Yep.
Thank you.
Oh,
Yeah,
thanks,
thanks.
welcome, Kelly.
No problem. Fall 2012. Which question? Yeah, thanks. 3?
Yeah.
Okay. Compare the values.
So, well, the second one and the last one.
Okay. What is, let me do like another. Okay. Oh, okay, sorry. All right. End of recording.